Welcome to this case study on feature engineering selection. We're going to be using a lithium-ion battery case study where we try to predict the crystal structure of the lithium-ion battery material, and we're going to classify that as either triclinic, monoclinic, or orthorhombic, although there are others as well, such as tetragonal, hexagonal, and cubic. We're going to use feature engineering. In this case, feature engineering simply like taking categorical data, such as a true or false, and turning that into a 1 or a 0. We'll also take the compound information for the lithium-ion battery and turn that into something that we can use for a classifier. We'll compare the results of the classification with and without this type of encoding. When we just throw away categorical data, we only use numerical data, we give away a lot. So we want to be able to use the information such as the chemical formula, the subgroups of the chemicals, and I'll show you how to do that with packages like ChemParse and others. So let's just go ahead and jump into this. We have feature engineer a little bit more on this notebook. If you want to go back and get the source code to this, just come to this web page right here. It's going to be in the description of the video, and you can see there's a little bit of background information such as lithium-ion batteries. They're commonly used for portable electronics, electric vehicles, and aerospace applications. They're becoming more important. And during discharge, lithium ions move from the negative electrode through an electrolyte to the positive electrode to create a voltage and a current. During the recharging, the ions need to migrate back to the negative electrode. And the crystal structure, as we mentioned, the monoclinic, orthorhombic, or triclinic, is available for 339 different chemicals that contain lithium. And the available properties are such as a material ID, that's just going to be a unique ID, the formula, this is the chemical formula of the compound, the space group, the symmetry group of a three-dimensional crystal pattern. We also have formation energy. This is the energy required to produce the material from standard elements. We have the energy above whole. Energy release if the compound is decomposed into the most stable compounds, the band gap. This is how well it conducts. Okay. The end sites, the number of atoms in the unit cell of the crystal, the density, the volume, and whether it has band structure or not. So you can get all of this data just by selecting this link, and you can see the 339 different compounds. And from these, we want to be able to predict this very last row, and that's the crystal structure. And if you want to run this in Jupyter Notebook, just come here, and this will take you to GitHub. You can right-click, save link as, and then save your Python notebook. The other way to run this is to come here to the Jupyter Notebook in Google Colab, and it'll open it up. You can just run it through a browser. You don't need to download Python. All right, and the three that we're going to be dealing with today, trying to predict, are one of these three: triclinic, monoclinic, and orthorhombic. Okay, so let's just go through this in a little bit more detail. We're going to, first of all, just go ahead and import ChemParse. This is a package that we need that is not typically distributed with Anaconda. So I'm just going to try to import it, and if it's there, then it's going to just import it without going to the accept. If not, it'll go to this pip install ChemParse. And what you need to do is, if it does install this, just come up here to kernel and restart and clear output. Okay, so that will help you use it. If you run it again, it'll see that it can import ChemParse and it will skip the install. Going on to the next one, we need to import some of the libraries. We'll get pandas, matplotlib, seaborn, and then let's get the label encoder and min-max scaler. We'll also get a train test split, a feature hasher as well, and our confusion matrix and plot confusion matrix as well. We'll import a decision tree classifier. So if you want more information about feature engineering, there is more information. You can get that again from here is the lithium-ion batteries right here. And then if you come up to features right here, you'll see just a lot more information on feature engineering. We're going to cover just one more today. There's the 3 ordinal encoding, 1 hot encoding. We'll have feature hashing, but then we're also going to decompose one of the features, which is the chemical formula, into its basic elements and be able to count those. So that's why we need chemparse. So it's like a physics-based encoding of some of the features. Okay, let's come down here. I'm going to run restart and clear output. Okay, and then if I just run this one again, Control Enter, I can see that I'm running these. Okay, and it's completing successfully. All of those packages are there. Now let's go ahead and load the data and display it. There's the URL for the data, and we're just going to use a pandas read CSV, and then we'll sample 20 of those values. So if we run this one, we'll see the table. Now this was the imported from the text file and made into a data frame, and you can see a chemical formula. Here's a space group, there's the formation energy, and you have others as well. And you'll see some of these, like has band structure, is a true or a false. You can also see the crystal system is a monoclinic, triclinic, or orthorhombic. All right, we just sampled 20 of those 339 values. Now let's go ahead and just look at the data types that we have. Okay, so the data types we can print out for each column, whether it's an object, and you can also see float 64, also int 64 as well, and a boolean here, true or false. So we're going to separate into numerical features and into categorical features that need to be transformed. So the numerical features are going to be those like the int 64 and the float 64. So those don't need to be transformed necessarily. We also have the categorical features. These are going to be our objects and also the Boolean value. We could put those as like a 0 or 1. Sometimes you can just convert those, but let's go ahead and convert those to integers ourselves. Okay, so we have our numerical features and categorical features. And let's go ahead and just describe the categorical features just to see what we have and what we're working with. Okay, so we have 339. Now one of the things you see here is we have 339 unique values for materials ID. So this means that it's not going to be useful to us for classification because we have no predictive capability of if each of those are unique. Also in the formulas, we have 114 formulas. So about a third of those are the same. Okay, sorry, about 3 of them on average are the same. So we're going to be able to split these into their individual atoms and be able to use those instead. Okay, space group, we have 44 on the space group, has band structure 2, and then crystal system, we have 3 of those. Okay, so let's go to the categorical encoding methods. We have one hot encoding. Now this is going to create a separate column for every category, except if you have a 0 or 1, true or false, it'll just be 0 or 1 for that. Okay, so it's simple to try to transform these into categorical features into these numerical features, although it creates many additional columns in our data. So it can make this very large, especially if you have many different categories, unique categories. You can create many different new features. Okay, we also can encode to ordinal values. Okay, so in this case, let's say our space group, we had 44 of those. We would just order them 0, 1, 2, 3, up to 44. Now, we can sort those to say, hey, this is more common, and maybe that's an interesting feature for this. But in general, if there's not enforced order to those, the machine learning or the data, the classifier may degrade if you use ordinal encoding when there shouldn't necessarily be an order there. All right. Feature hashing is kind of a compromise between the two, between one-hot encoding and ordinal variables. It creates a reduced subspace. And so one example that I'll give later is, if you have photos of apples, oranges, or there's a photo with an apple and orange in it. So you can potentially reduce that down in a way that you don't have to have individual categories for apples, oranges, and apples plus oranges. Okay, but this is a way to reduce it down into, maybe these 44 just into 3, a vector of 3. So for example, you could have 1, 2, -1, and you could specify the number of columns that you want. So unlike the one-hot encoding, it's going to create a new column for every unique feature that you have in that column. This one you can specify, hey, I want 3. Okay, so it makes it lower dimensionality, and it's a compromise between the two methods. Okay, so the fourth one that we're going to be introducing here is about prior knowledge about the data set. So we're bringing some knowledge about chemical compounds. For example, instead of just the chemical formula, we're going to break that down into number of atoms. All right, let's look at our materials ID column. This one, we have unique 339 unique values. So there's no useful information here. We can drop it. So let's go ahead and just drop it from our data. And there are the remaining columns that we had. So we just dropped that one. We selected in place. So we just operate on this data frame. All right, let's look at has band structure as well. And let's create a plot of this. So we say true or false. So here we have, many more are true and fewer are false. The imbalance in this really isn't a problem. If this helps predict the crystal structure, then we want to keep it. So we have 2 unique values, true or false. And so this is one-hot encoding or ordinal encoding are kind of the same here. You just basically create a new column with the 0 or 1. All right, so here's our 0 or 1. And we've created has band structure. We've mapped it. So any trues are equal to 1, any falses are equal to 0. Now let's look at our space group column that had 44. And here are the number of unique ones. P1 is the most common with about 73 or so. And you can see some of the others that are less common. Some of these down here around, 1. Unique one, so we're still going to include those, but they may not be able to predict that accurately. What is the crystal structure based on this, unless you had some of these as well in the test set. Okay, so the first option is one-hot encoding. It's going to result in 44 new feature columns. This is going to be very inefficient and memory intensive. Option 2 is to encode to ordinal numbers. So we just line them up. So first one gets the value 0, next one 1, 2, 3, 4, etc. But that leaves this residual structure that may affect the model performance. So we don't want that. So option 3 is use feature hashing. And we're going to compare these two, see how well they do. Okay, so first one, one-hot encoding. These would be the number of new columns that would be produced and added to the feature set. So we're not going to use this. All right, the next one is going to be ordinal number of encoding. And this one, it can be used with pandas factorize, and we're going to factorize the space group. Okay, and we can also order by the most common to the least common. Okay, so let's just go ahead and leave them in in that. Okay, and we're going to put these as integer type. Okay, these are going to be integer 32 right now. All right, and then the next one is feature hashing. Let's say we wanted just 3 columns. We're going to create our feature hasher with number of features equals 3, and our input type is going to be a string. And we're going to fit transform the space group, and we'll convert it to an array, and then we'll convert it back into our data frame, and we'll give those names, space group 0, 1, 2. Okay, we'll join with the original data frame, and let's just go ahead and get our head here. Oh, I already ran that once, so it joined it back to the data frame. I probably had a repeat on there. Okay, so I can only run that once. I've already run it once. Let me just go ahead and kernel restart and run all. If you run that one again, it tries to insert those again, and it's going to create a problem there. So here it is running it again, just restarting, and you can see the 3 space groups from the feature hashing. You can also see the space group ordinal, and then you can see the has-been structure, how we converted that to a 0 or a 1. Now let's go down to look at our formula column. So this one right here. And this is where we're going to use chemparse. We had 114 unique values, and let's just do a value count here on how many we had for each one. So you can see the top one, 42 of those. All right, so let's use this 4th option using some domain knowledge about chemistry. So we're going to use the chemparse package, and we'll apply, this is going to be a chemparse formula, and we'll convert the dictionary, this chem data dictionary, into a data frame and fill NaNs. So if the that element does not exist, it's going to be an NaN. So we're just going to fill those in. We're going to do JSON normalize. So we're going to convert that back into a dictionary, and then we're going to fill in the nada numbers with 0. So if it's NaN, it'll just become a 0, and then we'll join it. In this case, I'm going to do data head just so we can see these. All right, so if we come over here, we can see I've created lithium, manganese, silicon, oxygen, iron, and cobalt, and you can see the number of atoms in each one. And it did that for all 339. Okay, so let's do the final one, which is our crystal system. We've converted all of these except crystal system into numeric values. And this is our target column, the target label that we're trying to predict. We have 3 different types of crystal structures. So there are 2 options for this. You can either do a multi-class problem, where there's only one distinct type of classification, or you can do a multi-label problem. Okay, so multi-label problem, it would be a vector representation. So you'd have a different column for when that, for example, crystal structure is present. So for example, in the photo of an apple, you'd give it a 1, 0, or an orange, you'd give it a 0, 1. And if there's both in there, then you do 1, 1. In this case, we can't have both crystal structures. If we could use this method, but in this case, we're going to use a multi-class problem. Okay, so we're going to encode this crystal system to ordinal values. And here I'll take my label encoder, and I'll fit transform that. And here is the multi-label problem. We'd use one hot encoding for that. We'd get dummy values. Okay, so let me just insert a cell below, and let's look at our data. Okay, so here's the crystal system number. That's going to be the ordinal encoding, and then this would be the one-hot encoding, monoclinic, orthorhombic, or triclinic. So it would be a 0 or 1 if those are present. So two different ways of doing this. We're going to check for balance now. Probably should have done this earlier just to see if there's any that are out of balance in terms of the training. We can see that triclinic has the fewest at about 70, but it's not too far off these. This is about 140, 130, and then about 70. So there are methods to balance the data, but in this case, let's just go with the original data that's here. So I'll save the new features into a data frame. So when I run this, you can see I can open this up in something like Excel, and then we can see all of the new features that we've created and some of the original ones as well. Okay, so not save that, and I'll just come back to come back here. So let's go ahead and test the performance now. And we're going to have all numerical features. We'll exclude the crystal system because it's int 32. So we're just going to take the int 64 and float 64. That's just one way to sub-select the features. Okay, we'll have our ordinal features. And so there's the first set. And then we also have our hash features. Okay. Okay, so we're going to test the performance if we use an ordinal space group versus, these three for feature hashing. All right, let's get our labels. Is going to be the crystal system number. And so if I run this, then I can now create a plot, and we'll have with ordinal encoded. Okay, we're going to go through each of these. We're going to enumerate each. We'll have just numerical features only, ordinal encoding or feature hashing. We'll create our X and our Y. Okay, we're going to split it into 80% for training and 20% for testing. And then we'll create our decision tree classifier for each. We'll fit, and then we'll predict based on our test data. And then we'll plot our confusion matrix. So let's just go ahead and create a subplot for these 1 by 3, so 3 columns, 1 row. And we'll plot our confusion matrix. Create a heat map of that, and then give it a title. And in the end, we're going to save the figure. Okay, so these are the results. The original, if we just said, hey, we're only going to use numerical features only. We want high numbers here on the diagonal, and then on the off diagonal, we want to see 0 values here. But you can see that it didn't do a very good job of classifying the crystal structure when we gave up on some of those categorical data items. Now, here's the ordinal space group. So you can see that it classified everything perfectly on this test data. And then with encoded features, the hashed space group, you can see that there are some misclassifications. So overall, the ordinal space group and ordinal encoding looks like it did the best in this case, which was kind of surprising. I wouldn't think that space group would have, it would be able to exploit some of the all those values that were there. There was not necessarily an order that was helped to predict. All right, so these are the results. It basically shows we can improve with decomposing our chemical formulas into elemental counts. We can take the has band structure, convert that from true or false to a 0 or 1. And then space group as well, we cluster those by the different space groups and assign them numbers. Okay, so after this, this is part of the feature engineering, one of the case studies that I showed here as well. There's just one other one, an exercise number 1, where you can take the temperature and then the temperature first and second derivatives as features as well. So there are different ways to be able to take data and create new features, or be able to combine existing features and create a new set. Okay, well, I hope you've enjoyed this case study. Look forward to working with you on other modules here in the machine learning course.